Hello everyone and welcome to Conf 344, come back. Today we're going to continue or have a more definite introduction to query language. Last time we had a rough introduction to some query statements, the select statement and the update statement and search statement, which actually manipulated the data that's in the tables of the relational database. Today we'll see that using SQL, not only can we change the data inside those tables, but also we are able to change in the structure of the database itself, that is the structure of the tables. We can add more tables, drop tables, alter tables, using code. We can do that graphically and using code, using SQL queries. To have a more definite definition, we know that a database is a set of relations, and the relation is a table. The schema is the description of these tables, what kind of data that can be in there. Can be stored in those tables, and an instance is the data rows or tuples that are put in the tables and that satisfy the schema that describes those tables or that describes the database. So the terminology attribute refers to the columns, tuple is the record or row. I wanted to have a review over these definitions that we're going to use throughout our lectures. So the SQL language has two sub-languages, as well as, again, we have discussed all of these roughly in previous lectures. We wrap things up in this lecture to be more specific and more accurate. So we have data definition language. That's where we define and modify the schema, which is the structure of your database, and data manipulation language, in which we can query and change in the data that is in our database, and the queries that result from that we write in this SQL language is going to be executed by your relation database management system, and it's up to the relation database to choose which algorithms and which procedures to execute those queries. Whatever is the algorithm, the choice of the algorithm taken, it will have the same effect on the resulting data. I wonder, we have seen these examples, I suppose, before the same database. We have sailors, boats, and reserves, in which a sailor reserves a boat on a certain day, as you can see. So this is a very simple database. What you are going to do, your mission or your assignment, is for this lecture is to actually implement this database and apply all the queries that we're going to take on it. So you have to send them to me and to Ms. Huda, and there will be also an assignment on these same queries for the database, the small database, the airplane, airport database, and flight database that we saw last time. So we're going to apply on both this database and the other database. That would be your mission. And you are all encouraged to work throughout this course that I asked from you to build up your grade in the course. Okay, so these are these tables. So to create these tables, we did them we can do them graphically, and you can do them graphically, but we're showing here that you can also, and we've seen it before in a rough definitions and examples. So you can do it either in code or graphically. So here we're creating table sailors. The SID is an integer. The SNAME is a string of characters. Rating is an integer. Age is a real, and the primary key is SID. And we also create table boats with BID, boat ID, boat name, color, and the primary specify the primary key, and table reserves. Okay, we're specifying here in table reserves that the three keys are actually the primary key. Now we want to have two foreign keys, which are the SID and BID, that relate table reserve to table sailors and table boats. And in order to do that, we have to add foreign key. I said again, we can do that graphically as well. So foreign key SID references sailors SID. So this SID of reserves refers to SID of sailors, and BID of reserves refers to BID of boats. Okay, so to do that, you use the foreign key relationship and you use this syntax. All right, so that was data definition language, that's DDL, as you can see, because we are defining the structure of my database. In here, this is an example of data manipulation language. Okay, so for example, find all 27-year-old sailors. We select star from sailors as S. So S represents the sailors table, where S.age equals 27. This query should give me this whole table of sailors, because I said here select star, which means all the columns. Okay, that satisfy S.age equal 27. So I will have the output of this query. Okay, the select star will select all the table, but from sailors, but because we put this condition, then it will have only the last row, which is Nancy, as the output. Okay, so this row would be the output. So to find just the name and ratings, we replace the first row with only s.s name and s.rating, and this will do a projection of the selection on these two columns. So the same thing, but I would only have Nancy and 8 in that case. So let's now talk more about that definition language. So this is how you create a table. You need to put the table name, and we have to put the columns name with their data types. So speaking about data types, in MySQL we have many data types. I put you a link here to refer to into more details about these data types. But more generally, you can have character of fixed length n, that's character. You can have a character varying, that's varchar, yeah, and that would be of variable length character string, which means you can have n as a maximum or less. In this one, it was fixed length character string. You can have a binary of length n at text. We have binary object, which we usually use it for audio and video. And you have medium binary object, medium text, small integer, big integer, numeric. You can have date, time, and timestamp. So you can you have serial data type as well. So you can check those data types more if you want more on those data types on the following link of MySQL. So constraints, we have had discussions about constraints. We said that the schema defines the legal instances of the relations, and when I say instances, which means the data entities, the the data that's inside your database. It has to be legal, and to be legal, this means that the allowable data has to satisfy certain constraints. The first constraint that comes to your mind is the domain constraints or the data type. Okay, so the data type, which we talked about in the previous slide, is a way to limit the kind of data that can be stored in a table, but we really need more on that, and that's where we use constraints. Whether one of the constraints are the referential integrity, uniqueness, okay? So we can specify constraints per columns of a table. So let's talk about integrity constraints. I know we have discussed those, but this lecture is being more specific and how we do it in MySQL. So integrity constraints, conditions, gives me the conditions that every data item or instance of a relation must satisfy. So what does that mean? This means that upon insert statements, delete statements, and update statements, these integrity constraints are going to be checked. If upon insertion, deletion, or update, any of these integrity constraint is violated, then the statement is not executed. Okay, what does this do? This ensures application semantics, which means it ensures the correctness of the behavior of my database according to the application that it represents in real life. And another is to prevent inconsistencies. Okay, for example, the age is supposed to be less than 200, so we are making sure that no garbage data that doesn't make sense is inserted to my database. And this is of very high importance. We have different types of integrity constraints. We have the domain constraints, which are the data type, that is, primary key constraint, the foreign key constraint, and we also have general constraints. So always the field values must be of the right types. This is per column, of course, so this has to be always enforced, in that if you insert the data that doesn't satisfy, which is not in the data type that's supposed to be, it will not be inserted into the database, or the queries involving this item are not going to be executed. And of course, the important primary key and foreign key constraints, and this is a formal definition of primary keys, which is a set of fields, is supposed to be a super key if, so when are these fields are called a super key fields, which are columns, when no two distinct tuples can have same values in all these fields. So any two tuples are supposed to be distinct. So we said before, each record or tuple in a database, in a table, has to be different from another. They have to differ minimum by one key or one column, okay? Because no two tuples of the same values are allowed in a database. So super key is where these keys are unique, okay? So these are the unique key per tuple, like a primary key, but this can be a set of fields. That's a super key, more than one key. A set of fields is a key for relation if it's minimal. So we will always try to find the minimal the minimal unique key. So this minimal unique key, okay, will be called the primary key, which is a subset of the super key. So what if we have more than one key for a relation? That's for a table. You have more than one key, which is a super key, and it doesn't have a subset, so it's a minimal key. If you have more than one of those keys, okay, then one of them is the primary key, and the second one, we call it a candidate key. Very straightforward stuff. For example, student ID is a key for students. How about name? Since name can be the same between two tuples, that's why name is not a primary key. The set SID, student ID, and GPA is a super key, but I cannot make it a primary key. Why? Because SID alone can be a super key. Yes, so because SID alone is a unique key, now I have to have SID as the primary key, because we said the primary key is a super key, the minimal super key. Okay, so SID and GPA is not minimal, SID is a primary key. However, SID and GPA is going to be also unique per tuples. So you can have many candidate keys. We specify them using the unique keyword in SQL. One of these is chosen to be a primary key. However, the selection has to be, as we said, you have to be careful when you select your primary key. For example, in this example, enrolled, that's showing students enrolled in courses. The correct way to do it is to have the student ID and the course ID as the primary key, and I've seen this example before. Another option, enrolled to, is to have the primary key SID, student ID, and the unique key course ID and grade. In this case, that's a wrong interpretation, because in this example, you're saying that for a certain course ID, only, let's say, 1A is allowed, because course ID, let's say comp344A, this is unique for each tuple. This means that comp344 can have only 1A, and that's not what I want. So you always try, you be careful, and you check your semantics. So this doesn't satisfy my aim of enroll. This table, however, does satisfy the aim of enroll. When we talk about foreign key, we called it a logical pointer, because it's setting a relationship between relations, and foreign key are used in order to satisfy referential integrity, to make sure that the relationship between tables is satisfied. So a foreign key is a logical pointer where a set of fields in a tuple in one relation refer to a tuple in another relation. Okay, and it usually always, a foreign key in one table refers to a primary key in another table. When all foreign keys constraints are enforced, we call this referential integrity, because we don't want it to refer to something that doesn't exist. Referring to something that doesn't exist is calling dangling references, and enforcing referential integrity will avoid dangling references. So foreign keys are done in SQL, or you can do it also graphically. So for example, only student listed in students relation should be allowed to enroll for courses. And we have seen this example also before. To do that, this is enrolled. In the enrolled, we have a foreign key SID, so the foreign key SID in enrolled refers to students' SID, where students' SID is the primary key in students, so it's referred to by the SID. If enrolled, by enforcing referential integrity, you are making sure that no tuple is added in enrolled if the SID is not present in students table. For example, this is students table and this is enrolled. We can see that is there any student? So all the students in enrolled are present in students table, they are referred to them. However, if we add this, if we try to insert this tuple, it will not be allowed because this will refer to nothing and therefore it doesn't have a corresponding student in the student table and it will be rejected. So enforcing referential integrity, insert tuple with non-existent student ID. What will happen if we try to insert, to insert enrolled tuple with non-existent student ID, it will not be inserted. It will give me an error and it will not be inserted. Now, if you try to delete a student's tuple, what will happen? So this is how we enforce referential integrity on insert and update and on delete. So on delete, if you delete a student in the student table, you should also delete the corresponding tuples that refer to the student in other tables. That, for example, in this example, an enrolled table should also be deleted. So to do this option, there has to be the word cascade. So also delete enrolled tuples that refer to it. Again, what am I saying here? If you delete a student tuple in the student relation, you should also delete enrolled tuples of this same student and enrolled that refer to the same student. This is going to be done if cascade was put in enrolled. This allow in the referential integrity. This allow if referred to, this means that no action, which means that this allow the deletion of the student tuple if it's referred to from enrolled. This would give me, this is possible if the option was no action. Another option, so you have option cascade, which means if you delete the student, then delete all the enrolled tuples of the student. If you delete student, you will not be able to delete it. It will not be executed because there's the word no action in enrolled, which in the referential integrity in enrolled, which means that you cannot actually delete it. Third option, set SID in referring enrolled tuples to a default value. That is, for this student that was deleted, set it to, let's say, 000, a certain default. This would happen if the option was set default, so you can have any of these options. Another, the fourth scenario of enforcing referential integrity would be to set SID in the enrolled tuple to null, denoting unknown or inapplicable. That's done by using the keyword set null. So if it's set null in the referential integrity, then it will put it equal to null, which means it will put the tuples that refer to the student that was deleted. It will be, instead of the SID, which is the reference key, it would be unknown or inapplicable, which is null. Okay, so you will replace SID of the delete student with null if the option of referential integrity was set null. Okay? So we're saying that similar issue arise if primary key of student tuple is updated. So on update and on delete. So to see them more specifically, so create table enrolled. When we put foreign key, you have this option on delete, no action, on delete, cascade, on delete, set null, and that's the referential integrity scenarios that you can choose from. Another constraints, so we saw the domain constraint, the referential integrity constraint. Now, general and primary key constraint. General constraints now useful when more general integrity constraints, more than keys, are involved. For example, I have table sailors, I have specified SID, SNAME, rating, age, and I specified primary key SID. Now this check, so this SQL statement, if we add check to it when we create the table, check is actually a general constraint. We're checking that the rating value is greater than or equal 1 and rating is less than or equal 10. So on insert or update to this table sailors, there is going to be a check on rating. If it doesn't satisfy this condition, that rating is between 1 and 10 inclusive, then the query of inserting and updating will not be executed successfully. Okay. This is another way to do general constraint in that I'm specifying the constraint, I'm giving it a name. So you can give the constraint a name, and in the check we have something called, which we will take later, nested queries. Is in that in the check I have another query. Okay, so inside the query there's another query. We call this nested queries. We're checking that bname is not equal to interlake. Okay, so check that string interlake is not equal to b.bname from both b, where b.bid equals to bid. Okay, so we are checking here. I believe we'll get to that later because it's a little bit advanced. Okay, where we're checking the boat name. Okay, that's being reserved by referring to the boats table and getting the boat name and checking if it's different from interlake. Don't worry about this now because we'll talk about more advanced nested queries later on in the course. Constraints over multiple relations. So we're saying here that we can have constraints on more than one relation at a time. So for example, number of boats plus number of sailors is less than 100. So I have to deal with the number of boats and number of sailors together from two different tables. So create table. On this table, this constraint is checked when we add or update to table sailors. We're going to check whether count of SID from sailors plus count of BID from boats is less than 100. Count means the number, okay, the number of sailors and the number of boats, the count, okay, and because this is the primary key, so these are going to be the number of sailors in sailors, which is going to be the number of rows, and here's going to be the number of rows because it is the primary key. Now, the problem with this constraint is that it's only checked when we add to or update, when we have an insert statement or update statement on sailors. So this is going to be checked on sailors. However, it should be checked on both sailors and boats. And that's why we should actually create something called assertion, okay, which is going to be checking on both tables. However, this assertion is not actually, it's not supported in many DBMSs. We will address them in triggers later on as triggers. Other data definition language statements, you can alter table in a way that you can add, remove columns, change in the constraints, rename tables, rename things, rename columns, drop, but of course you have to compensate with in query statements according to what changes you do. You can delete tables, delete views, delete, create indexes, give privileges and remove privileges. So many many queries that you can change mostly everything in your database structure. Having seen all of these about DTL, let's now look at DML, which is modification commands, data manipulation language. To start with, we will start with delete. So we can have a delete only. So for example, delete from account. In this case, it will delete all tuples in account, or you can delete from account but with a where clause. And in this where clause, you can have actually a condition on which tuples to delete. Okay. For example, as you can see here, again, you have a select inside a delete, okay? So where bname is in select bname from branch where bcity is equal to Brooklyn. So an option is to use where and in, and in this case you can have another query inside the delete where clause, okay, and that we refer to another table which is branch, okay, and we selected bcity equals Brooklyn. A little bit advanced at this point. Okay, you will see now insertion statements. Insert into. There are different ways to do it. You can simply write insert into account, and you put the values that you want to insert. Or you can say insert into account and you specify the column names and then you put the values. They will give you the same result Another way is to have insert into with the query expression. Again, we're having query inside a query. Insert into account, select b name, where b name equal to Kenmore. So it's gonna go to the loan table, and for each Kenmore, whoever b name is Kenmore, we're going to add to him a savings of 200. Okay, so this is as if this insert statement gives 200 saving accounts for each where, you see the where clause, for each loan holder at Kenmore. In each loan in the loan table where the B name is Kenmore, we're going to add for this an account of 200. A little bit complicated. All right, so we'll continue with update. So update notification commands, usually every update comes with a set. So update table name, set attribute equal to a certain expression, and you have the where clause. Okay, so update account, set balance equal to balance times, let's say 1.06, where balance is greater than 10,000. This is another update here where balance less than or equal 10,000. So these are two different update statements. You can also have them in one statement saying update account, set balance equal, and you open a bracket, close bracket, and use the case clause. So case, when balance is less than or equal 10,000, then balance times 1.05, as if this equal here is to balance times 1.05, else that is the opposite of less than or equal, which is greater than 10,000, then balance is equal to balance times 1.06. Let's look at more single relation queries. That is, we want to work with queries on a single table, which indicates that in the next lecture we'll start doing queries on two tables, joining two tables. So basic single table queries, you have the select statement. Let's look at these different clauses. So simplest version is just straightforward. The select produces all tuples in the table that satisfy the where clause, the predicate clause here. The output would be whatever column list you have in this expression. Okay, so it could be a column reference or it could be an arithmetic expression. We'll see examples of both in this example. You have select two columns, okay, from student as, where as dot department, that's the predicate part, is equal to computer science, and this will show me only these two columns of this selection where the department is computer science. When we talked about let me see it again. Okay, and here we use the distinct flag, which means it will only show me the unique name and GPA, in that if there are the same name and GPA, it will not show me. So it specifies removal of duplicates before the output. Another clause is the order by, so select distinct as well. Here we have arithmetic expression on the column s.age, in that I'm multiplying it by 2 and I'm renaming it. The as clause is used for renaming. I am renaming it A2. So select will give me, in here the output will give me 3 columns. From students, this is the predicate clause, and we can add the order by clause. This order by allows you to order the output lexicographically according to the first column s.gpa. If you had two values that are the same, then it will check s.name. If s.gpa and s.name are the same, then it would look at A2. Okay, that's the order by clause. More on order by clause, it's showing you that you can mix and match in the lexicographic order, in that you can specify if it's descending or ascending. Okay, ascending is always the default, but if you put descending, then it will be descending, and if you put ASC, then it would be ascending, and this means that the order is going to be of descending GPA. If both are the same, we will order in ascending as name, name as dot name. Aggregates are very important in SQL in that we can select average s.gpa. In here, we're going to get only one value, which is the average of the GPAs where the department is computer science. So this will give me one row, which is the value of the GPA. One row and one column, which means one value. This computes, call it a summary. Other important aggregates are sum, count, max, and min. So instead of AVG, average, you can use any of these aggregation functions. You can also put distinct inside the aggregation function if you want to count distinct names or according to your application and to your query. Now let's look at the delete. We want to delete the records of all accounts where the balances are below the average at the bank. So delete from account where balance is less than, select average balance from account. This is possible in SQL. We can write it like this, but there would be a problem. So as we delete tuples from deposit, as we go on deleting, the average balance will change, and therefore we will have some invalid queries, invalid deletes. So how is this solved? It's already solved in SQL in the way the SQL algorithm is executed. So the SQL algorithm will first compute the average, save this average, and find all tuples to delete. Next, it will start deleting the tuples instead of deleting them and computing the average on each delete. Instead of that, it will compute the average first and then start deleting without computing the average again. So the group by clause, with group by usually we have aggregation select statements in which in here I'm selecting the average. So we are aggregating on getting the average function. So we're getting the average GPA of certain departments. Group by department, which means when you select the table, okay, from students, the table student, we're going to group to find similar departments. So for each department, for all the students in one department, that's what I mean by group by department, we get their average. So the output is going to be the average, okay, and the name of the department. So the average of student GPA of the same department. So for each group by each department, all rows that have the same department value will get the GPA and output the GPA for this department. Okay, so that's why the cardinality of the output is going to be the number of distinct group values, in this case the number of departments. Let's say if I have 5 departments, then for each department of those 5 departments, the average student GPA is computed and its output, the average along with the name of the department. Okay, we're saying we can group by a list of columns having a certain department, let's say, and another ID of a department together, for example. We can put grouping columns in select list. So for aggregate queries in the select statement, you can only have the aggregate groups and the columns only. That's the only thing that you can show. You cannot show the student name, or else you will, because you're going to output, let's say, 5 rows. If I am to put the student names, that would not fit. So usually in a select statement with the group by and aggregate functions, okay, we only have these columns only. Okay, we cannot have more columns like student name and other details, because the cardinality is only the distant group values of the output. So the having clause, it's used with aggregate and select statements. Okay, group by and select, we can use having. Having is only used with aggregate queries, that is having such functions, aggregate functions. So having is applied after grouping. After the grouping is done and the aggregation is done, then having is imposed. Okay, so it can only work on whatever list you have in the select statement. Okay, so that is the aggregates and the group by columns. That's the only columns that you can have, that you can apply having on. And so here having the count greater than 5, and we're saying that the having clause is optional. So putting it all together, the select statement, select as dot department, average of the GPA, count star of each having the same department, okay, from student S, where S dot gender is equal to F. So the clause here is on the gender, which has to be a female. Group by department, so rows that have the same department, we're going to compute the average of them, and we're going to count how many for the same department, how many tuples there are. It has to be greater than 2, and it's ordered by as dot department lexicographically, how they're going to be shown in the output. So conceptually, how does this evaluation take place? Actually, the SQL execution starts from, because that's where the table is. They have to look at the student table. After that, the where clause to eliminate rows where they don't have gender equal F and keep only those with gender equal F. For those rows, I'm going to project only on the needed columns. The needed columns are as dot department and whatever is used by group by and having, which is also the aggregation function, group by. Okay, and having, so we group by the same department name. So we group rows that have the same department name. Okay, and we eliminate those groups that don't have the count greater than 2. So we keep those that have the count greater than 2. So distinct, if you had the word distinct, then this would be the last step of the query. Okay, guys, you are all supposed to implement these queries that you have encountered in these slides and send them to me and Ms. Huda by email, as well as you will be provided with another assignment that have application of these queries on the airplane, airport, and the flight database, travel database that we introduced last lecture. I want you all to follow up. Okay, keep following up, and please do the functions that are required from you. See you next time.